In this video, we're going to talk about theory of logarithm. There is an existing relationship between indices and logarithm. In general, if n equal to a raised to the power of x, then the log form of these indices is going to be log n base a equal to x. That is, the logarithm of any number n to any base a is the power or index x to which the base must be raised to equal to the number n. Let's say if 1 equal to 10 raised to the power of 0, then taking this to log form is going to be log 1 base 10 equal to 0. So we can easily switch between the log form and the index form. That is 10 raised to the power of 0 equal to 1. If 1 equal to 10 raised to the power of 0, this is absolutely one of the laws of indices that says anything raised to the power of 0 equal to 1. And then, in the same vein, if 10 equal to 10 raised to the power of 1, of course, then changing this to the log form is going to be log 10 base 10 equal to 1. So the base always stays as the base of the log itself. Okay, log 10 base 10 equal to 1, or 10 raised to the power of 1 equal to 10. And the same vein, if 100 equal to 10 squared, and then changing this to log form is going to be log 100 base 10 equal to 2. So you can see that the base always stays as the base of the log itself. And then another way is if 1000 equal to 10 raised to the power of 3, and then we can say that log 1000 base 10 equal to 3. That is 10 raised to the power of 3 equal to 1000. So the existing relationship is that if n equal to a raised to the power of x, and then log n base a is going to be equal to a. So we need to take note of this, that the log to base 10, that is, if we have the log to base 10 this way, is actually called common logarithm. That is, the base number 10 is sometimes omitted. So we can, for example, if we're going to write log 100 base 10, it can as well be written as just log 100. If the base is not written, that means the base is 10. So it's a common logarithm. Log to base 10 is a common logarithm in theory of logarithm. And if the base of the logarithm is different from 10, it must be indicated. There is no common logarithm other than the log to base 10. Let's take a look at how we can use the relationship between the indices and the logarithm to get some questions solved. Don't forget, if n equal to a raised to the power of x, then log n base a equal to x. So we can actually use this concept to solve some of questions under theory of logarithm. For example, they ask us to evaluate this. We're to evaluate, let's say, log 81 base 3. If we're to evaluate log 81 base 3, we can just say let log 81 base 3 be any letter of a choice. Let's say it's equal to x. So if log 81 base 3 equal to x, and then changing this to indices, this is going to be 3 raised to the power of x equal to the number 81, using the concept we have here. If n equal to a raised to the power of x, then log n base a equal to x. So we can use this concept to solve this question. And then changing this to index form, this becomes 3 raised to the power of x equal to 81. And of course, if we have 3 raised to the power of x equal to 81, 81 is also the same thing as 3 raised to the power of 4. So in this case, we equate the indices. So equating the indices, we can choose to write them out just to show our steps. Equating the indices, since the base are equal, then definitely the powers must be equal. It can be equating the indices, equating the powers, or equating the base. Any of such phrase can go there, and therefore our x equal to 4. So definitely our log 81 base 3, the value of log 81 base 3 is equal to 4. Let's take a look at another example. Here we have log 32 base 8. And then we can just follow the same previous example, log 32 base 8. We can say let log 32 base 8 be any letter of a choice. In this case, I'm going for x. And therefore, we change this to index form. 8 raised to the power of x equal to 32 here. So 8 raised to the power of x equal to 32. And in this case, there is nothing we can raise to the power of 8 that's going to give us 32. But at least we can actually collapse 8 to 2 raised to the power of 3. So this becomes 2 raised to the power of 3 against x as the power there, equal to 2 raised to the power of 5. 2 raised to the power of 5 is 32. So in this case, we can write this as 2 raised to the power of 3x. That's 3 times x, the powers there, equal to 2 raised to the power of 5. So we can easily equate the indices. If you equate the indices, we have x equal to we have 3x rather, 3x equal to 5. And if 3x is equal to 5, then divide both sides by the coefficient of of x, and then our x becomes 5 over 3, which can as well be written as 1 whole number 2 over 3. Let's take a look at another example. Here is another one here. If log were to evaluate log 0.5 base 32, evaluating log 0.5 base 32, this can easily be done using the concept of the relationship between indices and logarithm. We can just say let log 0.5 base 32 be x. If it is x, in this case, then we change it back to index form. 32 raised to the power of x equal to 0.5. So this is 32 raised to the power of x equal to 0.5. And in this case, 32 is 2 raised to the power of 5 against the power of x there, equal to 0.5 here can be written as 1 over 2. And then here can be 2 raised to the power of x equal to 1 over 2 can as well be written as 2 raised to the power of minus 1. That's one of the laws of indices there. And therefore, if we equate the indices, since they share the same base, we can easily go ahead and equate the indices. In this case, we have 5x equal to minus 1. And of course, dividing both sides by the coefficient of x, our x becomes minus 1 over 5. So that is the answer to such a question. Let's take a look at another example. In this example, we are given if log 128 base 0.25 were to evaluate, if we're given log 128 base 0.25, we can just make use of the concept of the relationship between indices and logarithm. In this case, we let log 128 base 0.25 be x or y. So I want to use y this time around, and then we change this to index form. This is 0.25 raised to the power of y equal to 128. So this is 0.25 raised to the power of y here equal to 128. And then 0.25 can as well be written as 25 over 100 raised to the power of y, raised to the power of y there, equal to 128. This way. And then we can reduce that to its simplest form, 25 over 100. That can be 1 over 4 raised to the power of y equal to 128. And in this case, we can write this as 1 over 2 squared. That's 4 there, raised to the power of y equal to 128 can be 2 raised to the power of 7. And in this case, we can write this as 2 raised to the power of minus 2. We still have our y there equal to 2 raised to the power of 7. And then when you multiply the powers there, you have 2 raised to the power of minus 2y equal to 2 raised to the power of 7. So we ended up having the same base and the indices, and therefore we can easily equate the indices. Equating the indices, we have minus 2y equal to 7, and of course we have to divide both sides by the coefficient of y. So our y becomes 7 divided by minus 2, and then finally we can write it in its simplest form of minus 3 whole number 1 over 2. So that's the answer to such a question. Let's take a look at another example. If we have log 0.0625 base 4. So we bring the concepts of indices and logarithm relationship into play here. Therefore, we can just say let log 0.0625 base 4, let it be x. So if it is x, and then we need to change this one to index form, this becomes 4 raised to the power of x equal to the number we have there. So 4 raised to the power of x equal to 0.0625. So if it is 0.0625, this can just be written as 4 raised to the power of x equal to 625 over, since we have 4 digits after decimal point, that should be 10,000. Okay, and then we can reduce this, our 4 raised to the power of x equal to, if you reduce this 625 here, that should be 1 over 16. And then we can write 4 raised to the power of x equal to 1 over 4 squared. And then this can be written as 4 raised to the power of x equal to 4 raised to the power of minus 2. So in as much as they have the same base, the powers can be equated. So equating the indices there, our x equal to minus 2. So that is the answer to such a question. Let's take a look at another example. If we have, let's say we have log of root 128 base 2 root 2. So the concept is what will get this question done easily. That's log root 128 base 2 root 2. Let's represent it to be y. So if it is y, and then this raised to the power of y equal to the number. That's the concept of indices and logarithm relationship. So changing that to index form, this is 2 root 2 raised to the power of y equal to square root of 128. And then if we have this kind of scenario here, what we can just do is to square both sides. If you square both sides, you can just have 2 in order to get rid of the square root here. That is squaring both sides. We have 2 roots 2 raised to the power of 2, in as much as we have y there that has to be carried along, equal to square root of 128 square. That's squaring both sides. And then we have to be careful here in interpreting this. This has to be 2 square. The 2 will affect this, and then multiply by square root of 2 square itself. We still have y out equal to this square. Will get rid of the square root there. That's 128, and therefore we have 4. That's 2 square multiplied by 2. Okay, that's 4 multiplied by 2, and then raised to the power of y equal to 128. And therefore 4 times 2, that's going to be 8. So we have 8 raised to the power of y equal to 128. And in this case, 8 can be written as 2 raised to the power of 3, and of course it's going to be 3y equal to 128 is 2 raised to the power of 7. And in as much as the bases are equal, then we can easily equate the indices. That is equating the power. And in that case, we have 3y equal to 7. And if it's 3y equal to 7, we can just finish up our answer here. And therefore, 3y equal to 7, dividing both sides by the coefficient of y. And then we have y equal to 7 over 3, which can finally be 2 whole number 1 over 3. So that is the answer to such a question. Let's take a look at another example. If we have, this is log root 512 base 4 root 2. We simply use the concept of changing indices to logarithm and logarithm back to indices, the existing relationship between indices and logarithm. So we say let log square root of 512 base 4 root 2, let it be y. So if it is y, then changing this to index form, this can be 4 root 2 raised to the power of y in the bracket equal to square root of 512. And therefore, this one, we need to square both sides to get rid of the square root. So squaring both sides, that becomes 4 root 2 raised to the power of 2y now. That is, in as much as we have y there, equal to square root of 512 raised to the power of 2. And then this 2 has to affect all the contents of the bracket. So this one is 4 square multiplied by square root of 2 square, and then raised to the power of y altogether equal to this, get rid of this, and that becomes ordinary 512 there. So 4 square here is 16 multiplied by this, get rid of this, that's 2 raised to the power of y equal to 512. And in this case, 16 times 2 is going to be 32 raised to the power of y equal to 512. And therefore, 32 can be written as 2 raised to the power of 5, of course, y equal to 512 is the same thing as 2 raised to the power of 9. So in as much as they have the same base, and the powers can be equated. So equating the indices, we have 5y equal to 9, and then dividing both sides by the coefficient of y. Our y becomes 9 over 5, which as well can be written as 1 whole number 4 over 5, or we can write it in decimal as y equal to 1.8. So that is the answer to such a question. Let's take a look at another example. In this example, we are given log 0.2 base 625. So we can just say let log 0.2 base 625 be x. So if it is x, and then we can change it to index form. 625 raised to the power of x equal to 0.2. So 625 raised to the power of x equal to 0.2. And in this case, we can actually collapse this to 5 raised to the power of 4. That's 625. And then we have raised to the power of x there equal to, this can be written as 2 over 10, of course, because we have just a digit after the decimal point. And therefore, this can be written as 5 raised to the power of 4x equal to, reducing this to a simplest fraction, that's 1 over 5, which in turn can be written as 5 raised to the power of minus 1. In as much as they have the same base, the powers can be equated. So equating the indices, we have 4x equal to minus 1. So if 4x equal to minus 1, we need to divide both sides by the coefficient of x. So dividing both sides by the coefficient of x, our x becomes minus 1 over 4. So that is the answer to such a question. Let's take a look at another example. Here we have log 2.197 base 1.3. So we're still going to use the same concept, the relationship between the indices and logarithm, that is changing indices to logarithm and logarithm back to indices. Here we can just say let log 2.197 base 1.3 be y. So then changing this to index form, we have 1.3 raised to the power of y equal to 2.197. And therefore, this can be written as 13 over 10. That's 1.3 raised to the power of y. And this can be written as 2197 over 1000, because we have just three numbers after decimal points there. And therefore, this one is 13 over 10 raised to the power of y equal to 2197 divided by 1000. If you reduce this, you're going to have 13 over 10. That is using 10 to reduce this. And then raised to the power of 3. That's 13 raised to the power of 3 is 2197. And 10 raised to the power of 3, that's 1000. In as much as the bases are equal, the powers can be equated. So equating the indices, y is going to be 3. So when you are to evaluate log 2.197 base 1.3, the answer is going to give you 3. Let's take a look at another example. Here we have log 0.0004 base 50. Okay, so the same concept will be applied here. Then we can just say let's log 0.0004 base 50 be x. So in this case, 50 raised to the power of x, changing it to index form, 50 raised to the power of x equal to 0.0004. And then we can change this to a fraction. This is 50 raised to the power of x equal to, this is 4 over 10,000. In as much as we have 4 digits after the decimal point. Here is 50 raised to the power of x equal to 1 over 2500. And then here is 50 raised to the power of x equal to 1 over 50 squared. 2,500 is 50 squared. And then this can as well be written as 50 raised to the power of x equal to 50 raised to the power of minus 2. That's 1 over 50 squared is the same thing as 50 raised to the power of minus 2. And then we can see that the bases are equal, therefore the powers can be equated. So equating the indices, our x becomes minus 2. So evaluating log 0.0004 base 50 is going to be minus 2. That is the answer to such a question. Thanks for watching. Kindly subscribe to my YouTube channels.